All right. Welcome back. Everyone have a fun Labor Day weekend? Anyone do anything fun or exciting? Yeah? That's pretty good. That's the tallest one in Utah Valley, right? Cool. Sweet. Well, yeah, just a couple of announcements. We now have a physical TA office. So if you want to get in-person help on labs, they will start getting harder. And so we help to have that in-person, face-to-face discussion. The TA office is in 1152 TMCB in the Talmadge building. And Matthew just posted that on Slack. Also, I've gotten a couple of Slack messages asking me about recorded lectures when people are gone. In case you didn't know, all of the lectures are recorded and they're posted on the suite on the schedule tab under the day of class. So if you ever have to miss class, those are there. I don't make any guarantees that it will be the same experience as being in class, but the content is there. Yeah, question? What was that?
Did you also upload those?
Yeah, so the links on the schedule tab are links to you. All right. Before we begin, does anyone have any questions on Lab 2 due this Saturday or on things that we've been covering in the past couple of classes? Yeah. Absolutely. Yeah, and that's some feedback that I think a lot of people have had with this class. And it's never gotten officially introduced into the curriculum. Yeah, next week we will do some actual coding and talk about kind of what's happening under the hood of PyTorch, which I think will help you get a better idea of what's going on and also how to solve the errors that you run into. Good question. Okay, so we wrapped up last time talking about how we encode a real world objective into math. And we arrived at this softmax negative log likelihood loss function, or you could say like inverse success function. We'll take a look at this slide for a second and try to remember what each of the different things in this loss stands for. We get a volunteer to explain what this formula means intuitively. Yeah, Grant.
I don't know, maybe trying to match up like probabilities that have correct output.
Pretty good. Yeah, that's along the right lines. We had someone else in the back. Yeah. It's actually between negative infinity and 0, but very good. So you just, yeah, that's great. What was your name? Neil. Yeah, so Neil just told us how basically what this means in terms of probability. So the way you would say this is the likelihood for item I, or the log likelihood for item I is the negative log of the probability that y equals yi given that x equals xi. So what are x? What is x? What is xi? What is y? And what is yi? Yeah. Close. Yeah, I think you're I think you got it. So yeah, x is the input. And big X represents a random variable that represents our input. Little xi represents the particular input that we are providing to the neural network. So, for example, an image of a cat. Big Y is a random variable representing the output of the label for that image. And then little yi is the particular label for this image, which is cat. Yeah, and so we want to, what we're trying to do intuitively here is maximize the probability of the true label given our input image. And sometimes you'll also see this with a comma theta after this x, where theta represents the parameters of your neural network, or W. So you could say, yeah, x comma W or x comma theta, and that just means that the parameters of the neural network are also an input to this one. Does that make sense? Why we would choose this objective, and why learning this objective would help our neural network predict the correct output, the correct label? Yeah. Great question. Yeah, so mean squared error is another loss function. A couple of advantages of this, and there are also some equivalencies which we will go over later on in this class. So to answer your specific question, mean squared error usually used when you're predicting a continuous value as opposed to a discrete category. So if you were trying to predict the number of cats in this image, or predict how tall the cat in this image was, that's a continuous value. That could be between like 0 and 100 if you're picking units. Whereas this is a loss function for a discrete prediction problem. So where you have multiple categories, for example, cat, dog, train, boat, etc. Does that make sense? So there are different loss functions for different, whether you want to have a discrete or a continuous prediction problem. Okay, so moving on, we're just going to do this in real life. So this is what we call our score vector that our network has predicted for this image. We then apply an exponential function to each of these numbers. So this is e to the sj, and we get this vector. And then we normalize. So we take each of these. So this is S1, S2, S3, and we're going to divide by the sum of all of these. And this is what we get. We now get numbers that sum to 1, which we can now interpret as probabilities. From there, we pick out the number that came from the true class, and we, because the objective function is e to the syi, so we only consider the score for the true class, and we take the negative log of that. And that's how we go from a score vector to a negative log likelihood. Yeah, questions? Yeah, so the question is how we get from this original score vector to the unnormalized probabilities. And we do that by taking e, the natural number, raised to the power of each of these scores. And if you remember, we talked last time about how the reason you do that is because it makes all of these positive, but it's also a function that is monotonically increasing so that it still preserves the ordering of these. You'll notice that negative 1.7 is less than 3.2, which is less than 5.1. And so negative 0.18 is less than 24.5, is less than. Yep, question in the back.
So those, you're not taking the score associated with y sub I, which is the desired output.
Correct.
As S of y sub I.
Yeah.
Well, on the bottom you got S. But I'm assuming it should be S of y sub j.
Yeah, so this is just kind of, yeah, it's a good question. So the question is, what about these subscripts? Should this be S sub y sub j? And the answer is no, because j goes from 0 to 2, 0, 1, 2. And yi represents an item, an integer, representing the correct class. So in this case, 0, and that's taken from our data set. And so like y sub j would be the correct class for the j item in our data set, which is not correct. Because we're not indexing over our data set down here, we're indexing over all the different classes. Does that make sense?
Sure. So we take all the score and that score.
Yeah.
And so the numerator is score, right?
That is correct. Yep. Okay. Any more questions on this? Yeah. Yeah, all of the scores, including the original score. Yep. Yeah, including the score for the true class. So the score for the true class is in the numerator and the denominator. Yeah.
So let's say there were 10 images. You would find the SI of each individual category that actually want to reach or.
Oh, good question. So the question is about this subscript I on the L. So here you'll notice this I is the same as this I. So the I by the L is the same as the I by the yi here. And that's because this I indexes over the data set. So we'll have a loss for each image and label in our data set. Good. All right. And we already mentioned this, but we'll see if you remember. So what is the minimum and maximum possible loss Li? Can you explain why that is? Yeah. Very close. Very, very close. You want to explain your rationale? Yeah, so you're totally on the right track. So let's start here. What is the possible range of values in this probability vector? 0 to 1. And then what is the possible range? What is the range of possible values of this log of the probabilities? We're asking what the range is of the log function from 0 to 1. Over what values does log range when you're constrained to 0 to 1? Yeah? It's negative infinity to 0, correct. And then the negative log, oh wait, you're totally right. So I was thinking negative infinity to 0, but you're right. So it is 0 to positive infinity because we then take the negative of that. So yeah, you're right all along. Good thing we worked through that. Okay. Yeah, so the minimum is 0, the maximum is positive infinity. We will skip that question. Yeah.
After that one guy's question about should it be YJ? I think it is supposed to be YJ because the YJ is like the classification for the S like that of one, right?
So
we can talk about that later.
You're talking about
It's like
you think what are you think
so
this
like,
the SJ should be S of YJ?
yeah, because the Y is like the set of classifications, S is like the data point, and the J is the index of the classification.
Yeah, so this is so you would be right if we defined Y as a vector. But in this case, we're just saying Y is an integer. YJ is an integer representing the correct class. So if the correct class was fraud, then YJ would be 2.
So I don't understand why it wouldn't be that same unitary classification for on the bottom as it is on the top.
So it's because y, the subscript of y indexes the different items in the data set. And so if we are talking about y sub j, that would mean like the class corresponding to a totally different item in the data set. Does that make sense?
Yeah.
So yeah, we can talk about it later. We're still kind of fun. Okay. Yeah. Good question. So the question is there any, what here tells us what the right answer is? And the only thing telling us the correct answer is the fact that we select the true class, the correct answer, out of this final log probability vector. So that's where we get our training signal.
Nothing. It's just these are.
Well, so it does tell us the right answer because yi is the correct answer. Yeah, so the correct answer is in here, and that it's in the fact that we only take the log likelihood corresponding to the correct class. It's good to go over this because yeah, it's not. What if you were to write out a loss function? This is not the first thing I would write down on a piece of paper. Yeah, question in the back. So there's not a base that's specified for this log. So I actually don't. Maybe it's the natural log. Maybe it's base 2. Maybe it's base 10. I'm not sure. Gotcha. Yeah. So I mean, you could. Yeah. All right. We're gonna do another practice of this. So here we have our input vector xi. We have a linear classifier with learnable parameters w and b. And you remember, and this is something I meant to mention last class period. You can think of each row in w in the case of a linear classifier, you can think of every row in w as a prototype vector for that class. I was talking about this with Ben the other day. So you can think of it as like this is the, remember when we saw those mean images, like the mean image of the horse, and it had a horse facing one way and a horse facing another way. That image is what would be in this row of W, except it would just be stretched out. And so for me, it's just a helpful way to think of it is, yeah, the rows of W are prototype vectors for the particular classes. And then if xi is identical to that prototype vector, you can imagine that because when we multiply this matrix by this vector, it's the dot product between xi and that prototype vector. You're basically computing what between those two vectors. Similar, yeah, exactly, the similarity between your input and the prototype vector. So I don't know if that intuition helps. Going back to this, so here we have W, we have an xi, and we have a yi. Let's look at what we get out of this. We do matrix multiplication, add the bias vector, we get these unnormalized scores. We take the exponential of them, then we normalize to sum to 1. Then we take the negative log of the correct class, which in this case is 2, because yi equals 2, and that is our loss. Now you'll notice here that we're calling that loss something different now. We're calling it a cross-entity loss. What on earth is that? Well, it turns out that it's the same thing as the negative log likelihood loss. And we're going to explain why that is the case. And this is just to be clear. The cross entropy or negative log likelihood loss is not the only loss function we could have chosen here. You suggested the mean squared error as a loss. that wouldn't work for a classification scenario, but there are other classification losses, like this loss called the hinge loss. So just be aware that there are other loss functions out there. Okay, so yeah, now this section is called a couple of notes to avoid confusion. It might just confuse you some more, but we'll see if we can get through it. So we're maximizing log likelihood. Oh yeah, question over here before we go. Yes. Yeah. So the question was, when you print out the loss in PyTorch and you see a list of losses, does each of those losses correspond to a different item in the data set? And the answer is yes. Yeah. Dane.
So with the different loss functions, I think back to the 3.1 Brown video that we had reading last week, and it talks about how we're doing gradient descent, trying to find these valleys. Does changing the loss function change the amplitude of those sort of valleys?
Yeah,
Yes,
absolutely.
or
So
does
yeah,
it?
the question was whether, and we'll get into this very soon, is when you train a neural network, you're trying to minimize the loss function. And you can imagine the loss function as being this kind of bumpy surface over all of the neural network parameters. And the question was whether changing the loss function changes what that loss landscape looks like. And the answer is absolutely yes. And we'll see some visualizations of that later in class. Okay, so we took the log of our loss. Why did we do that? Well, it turns out that because the log function is an increasing function, the maximizer of the likelihood is the same as the maximizer of the log likelihood. But it just so happens that when you are when you're dealing with probabilities, especially when you have a lot of the time in deep learning, you'll have multiple probabilities multiplied together. It's very easy for those probabilities, you imagine taking 0.01 to the 10th power. Pretty soon you're running out of numbers that can represent that loss in floating point arithmetic in a computer. And so in order to avoid that problem of numbers getting vanishingly small, we take the log, which means that if we have multiple probabilities multiplied by each other, they are now added instead of multiplied, and the numbers end up being a lot larger. Yeah, question. Yeah, that's a way to think of it. Mm-hmm. So maximizing log likelihood is equivalent to maximizing likelihood. But we use log because it's more numerically stable. This part is probably obvious, but maximizing log likelihood is equivalent to minimizing negative log likelihood. And then this is kind of an interesting one. So negative log likelihood loss is equivalent to cross entropy loss. And you don't have to understand this beyond knowing that when you hear those two things, they are equivalent. But if you're interested, we'll get into this. And this is a good chance to practice your math. So the cross entropy between two probability distributions, P and Q, is defined like this. So X, so big X represents the number of classes. So this is we're mixing notation a little bit here. So we're summing over different classes or different classes or discrete probabilities here. And we're taking the probability under distribution A multiplied by the log probability of that class for distribution or distribution B, or I'm mixing the variables here. Distribution P and distribution Q, we sum over all classes and multiply the probability under P times the log probability under Q. And so we write this out. Let's suppose we have 3 classes. And we will say that P is the target, or Y. And this kind of gets into what Matthew was saying about notation. So if instead of Y being an integer, we make Y a vector with a 1 in the correct slot. And U is our predicted probabilities. Then this sum here reduces to basically all, because our target vector only has all of its probability in one class, all of the other terms disappear, and we are left with negative E yi times log. Okay, this pen is not working very well. But times the log of the predicted probability for the true class. Does someone want to try explaining that back to me in their own terms? Yeah.
So when you make you normalize the probability of the second then you're left with the true class having lots of value when you form the cross-section.
Close. So yeah, I'll try to restate that. So in the cross entropy loss, the true probability of all classes except the true class is 0. So you're only left with the true class, the probability of the true class being 1. And then all of the other terms in this sum disappear. So that you're only left with the 1 times the log probability, predicted probability of the true class. And that's written here at the bottom as well. And actually, this yi on the bottom should be outside of the parentheses. Because that indexes the predicted probability vector. Okay, yeah, we got a question over here. Yeah, you first.
Just wondering about our E vector. So bunch of zeros, 1, 1. We place the 1, which like we're is that the U vector?
Yes. Oh, no. So based on the label. So yeah, this is a good question. So this kind of thing that I showed here is called one-hot encoding. So a label of 1. So if we have integer labels like 0, 1, 2, you can map that into a vector with all zeros and then a single 1 under what that index would be. If we were to translate 2 into a one-hop encoded vector where there are 3 classes. It would be 0, 0, 1. And then 0 would be 1, 0, 0. So the different rows of the one-hop vector represent the different classes. Yep. And same with the prediction vector, those represent the different classes. And so we multiply this by the log of, we multiply 0 by the log of 0.2, and we get 0. We multiply 1 by the log of 0.8, and we get some number. And we multiply 0 by the log of 0, and we get some number. And then, so all of those terms disappear except the middle term. And we can see that here, it reduces to negative log q of x, index at the class, at the true class, which is the same as our negative log likelihood loss. So this is just kind of a nifty, different interpretation of the negative log likelihood loss. Okay. So to summarize, maximizing likelihood, and this is really the only thing you need to remember from this kind of mathy section. Maximizing likelihood is the same as maximizing log likelihood, is the same as minimizing negative log likelihood, is the same as minimizing cross-check. Question.
So left, we have to.
Yeah, and that'll be the easiest way to do it. Or I mean, it depends on which way is more intuitive to you, but yeah. All right, so this is where it gets fun. So we're going to talk about how do we minimize? We have a loss function, we have some real world objective encoded into math, and how do we train the neural network to achieve that objective? So we have a data set, we have a score function and a loss function. This is our log likelihood. And then this is a log likelihood with what's called a regularization term, which basically is another kind of trick to help training be stable. And we are going to use a technique from calculus called gradient descent. So what is a gradient? Well, let's go back and start with what is a derivative, because a gradient is an extension of a derivative. It's on the board. The derivative, if you remember from calculus, is you can think of it as the slope of a function that goes from r to r. Now you may remember that notation from the linear algebra lecture, where r represents the real numbers, and so like a simple function just goes from the real numbers to the real numbers. However, in deep learning, we're usually dealing with functions that go from Rn to R. So instead of having one x-axis, we have basically n x-axis, n x-axes. Here we just have 2, so this is just R2 to R. But you can imagine, or maybe you can't imagine because it's hard to imagine more than 3 dimensions. But yeah, you could have more axes that represent other inputs to your neural network. So a gradient is a vector of partial derivatives. So if you want to take the derivative of a function that goes from Rn to R, and instead of getting a single number that represents your derivative, you get a vector that represents your derivatives with one derivative corresponding to each of your inputs. So if you have n inputs, you're going to have n what are called partial derivatives. And so what we are going to do is follow the slope. So in math, what does that look like? Well, we take the current weight W of our neural network, and we subtract what's called the learning rate times the partial derivative of the loss with respect to that particular weight that is an input to the neural network, or that which is an input to our final loss. Yeah.
So learning rate, step size, or
Yes, learning rate and step size are synonymous. And so you can imagine that as you do this, you will gradually take steps in a direction that causes your loss to go down until you end up, hopefully, at the minimum of your loss. And yeah, so this is the math version, and then this is the version in code. So basically, for as many times as you want to go through a loop, you calculate a gradient by calling this function evaluate gradient, which takes as input your loss function, your data, and your weights. And what it will do is it will pass your data and your weights into your loss function, produce the loss, calculate the gradient of that loss with respect to the weights, and then assign it to this variable called weights grad. So weights grad now holds this number, the partial derivative of the loss with respect to each of the weights, and weights grad will be a vector. Weights grad is not a number; it's going to be a vector or a tensor of the same size as your original weights. So your original weights, you will then add negative step size or negative learning rate times that gradient vector. And that's it. You now have a trained neural network. Yeah, we did. Yeah, so you'll probably in your we wanted to make this a two-liner, but in your code you'll probably break this up into multiple steps. First, you will compute your loss function, then you will compute your gradients, and then you'll take a step on that. Yeah, you're right. That is a lot that's going on in that little. Okay. Yeah.
So just to summarize, make sure and the loss function for the gradient. The loss function is going to turn discrete classes into this continuous function that we change the weights to find the loss.
Great. Yeah. So the question was, yeah. So did you finish your question?
Yeah.
Okay. So the question was whether what exactly is happening with our loss function, and yeah, and I'll just repeat what she said for the recording. She said that basically the loss function is a way to turn that vector of scores into a single number, and then that we can then that is continuously valued. So we can then take the gradient of it with respect to each of the weights, and then we can tweak the weights to make the loss function go down. Yeah.
We're taking a step size that's a coefficient of this gradient as we sort of improve. Well, as we get to the bottom of the valley, the slope is going to decrease to zero.
Yeah.
So if you're taking steps on it taking an exponentially longer amount of time.
That is 100% true. Yeah, that is a great question. So Jane said, observed astutely that as you get to the bottom of your valley, the valley that you want to get to, your slope is going to become almost zero. And so it's going to be harder and harder to get to the right place. Part of that is solved by the fact that if your slope is getting very flat, then there's not much more improvement that you have left to gain. But then there are also techniques. So this algorithm for updating a weight is called gradient descent. There are other algorithms that try to solve these problems of how do you get through flat regions of the loss surface. and things like that. And so there are these things called learning rate schedules, where you increase your learning rate, then decrease it again, decrease it, and use it again to kind of like get past what are called local minima in the loss surface, to hopefully be able to get to settle into a deeper result. Yeah. Matthew.
There's actually a comment there's a comment about that in the general board on Slack. Me and Ben were answering a student question about that.
Great. Yeah, feel free to check out Slack if you want to know more. Dean, did you have a follow-up question?
Yeah, so I think then you really want your loss function landscape to be very curvy, because otherwise you can't really go anywhere. It's flat. There's a divot somewhere. You won't find it unless you have slope to get to there.
Yeah, question. Yes, so the question was, we have this super high dimensional space. Isn't it unlikely to get caught in a local minimum? Because there's probably some dimension that you can go along before you'll get some improvement. And the answer is yes. But that said, if you can try to smooth out local minima as much as possible, you will arrive to the minimum of your loss function a lot faster. So practically, you can probably get out of pretty much anywhere that you are, any local minimum that you're caught in, but it may just be that training is so slow at that point that you practically can't get out of it, and so you want to find ways to smooth that out. Okay, so in the last 5 minutes, we're just going to kind of put this all together in a big picture. So we have a data set, we have images and labels, we have a neural network, we pass our inputs, our images, into the neural network, which produces a predicted score for each image. We then take the predicted score and the true label, pass it into our loss function, and get the negative log likelihood of the true class. We then optimize the weights of our neural network by using gradient descent. And then we now have a trained neural network. Then when you are using a network on unseen images and not training it anymore, that's called testing. So we now take new images that the neural network has not seen before. We pass them through the network. It produces predicted scores, which you can then threshold and classify as being a cat or not being a cat, or being a cat versus being an airplane or a dog or whatever. So that is it. You guys know how to train a neural network. You'll still have to learn the nuts and bolts of PyTorch and all that stuff, but have the essentials. Yeah, question. Yes. See, this is a good question. So when you test, does it ever change your model? You don't want it to, because the whole idea of, when you train a network, you'll have a training set and a test set. And the purpose of the test set is to evaluate how well your model will generalize from the training data to unseen data. And so a test, like your test loss, is going to be kind of a good way to know how well your neural network will do on things that it's not seen. So you don't want to change it based on the test data, because that takes away the point of it. All right, we're going to do a quick quiz before we go. Which of the following are equivalent?
Yes.
So is A equivalent to B?
Yes. Yes.
Are A and B equivalent to C? No. Are A and B equivalent to B?
Yes.
Yes. So A, B, and D is the correct. All right. Thanks for coming.